Hello viewers, I am Kausalya. Today we are going to see an introduction about second order system. So this is a general representation of a closed loop transfer function of a second order system. So here C of s is your output and R of s is the input, and this is your standard representation. So here omega n square divided by s square plus 2 zeta omega n s plus omega n square. So here the denominator polynomial gives the order of a system. So here this is our denominator polynomial, right? Omega n square is numerator and this is our denominator. So what is the maximum power of s here? The maximum power of s is 2. So only we are denoting this one as a second order system. So here omega n is nothing but undamped natural frequency. The unit is radian per second. Here we all know that generally we will be representing omega as 2 pi f, right? Similarly here this omega n is some frequency and its unit is radian per second. And zeta is damping ratio. We will discuss in detail about damping ratio in the upcoming videos, and the formula for zeta is given as actual damping to the critical damping. This is a big topic. I'll explain while solving derivations for each and every type of system. And based upon zeta, the systems are broadly classified into 4 types, and they are undamped system, where the value of zeta is equal to 0, underdamped system, where the value of zeta lies between 0 and 1, and critically damped system, here the del is equal to 1, and overdamped system, and here the value of del is greater than 1. Right, so these are the 4 types of system based on zeta. And the next one, we are going to solve the characteristic equation of the second order system. So the characteristic equation of the second order system is, it is nothing but the denominator polynomial of a closed loop transfer function. So this is the denominator polynomial, right? S square plus 2 del omega n s plus omega n square, which is equal to 0. Now we are going to solve this equation and we are going to find the roots. So this is a second order equation because the maximum power of s is 2. So we will be finally having 2 roots. So the formula to find the roots are minus b plus or minus root of b square minus 4ac divided by 2a. So this is a formula. So here from this equation, the value of a is nothing but coefficient of s square, it is 1. And here the coefficient of s is 2 zeta omega n, and the value of c, that is the constant, is omega n square. So here just substitute the values in these respective places. So here you will be having the value of b is 2 zeta omega n, right? So minus b plus or minus root of b square. So this is your b. So b square minus 4ac. Value of a is 1 and c is omega n square divided by 2a, right? And the next thing, I am going to square this term. So 2 square is 4 and del square omega n square. Minus, here you are multiplying 4 into 1 into omega n square. So here I am having 4 omega n square divided by 2. And here again minus 2 del omega n plus or minus, you see here in this term I am going to take 4 omega n square commonly outside because this is present in both these terms. So when you take 4 omega n square, the remaining term will be del square minus 1 divided by 2. And again when you take this square root for 4 omega n square, the square root of 4 is 2, and for omega n square this is omega n, and the remaining terms as such. So here now the 2 is present in both the terms, the denominator, so we can cancel these 2's. So the remaining term will be minus del omega n plus or minus omega n into root of del square minus 1. That is, this is the root of the characteristic second order equation, right? And the next thing is we are going to classify. I'm going to explain for the 4 types of system how the values will be. So here this is the general expression for the roots. And here for the first type of system, that is, this is your root equation. And the first case we have seen for an undamped system, the value of del is equal to 0. So when you substitute the value of del as 0, look here, when you substitute zeta. When you substitute the value of zeta as 0, here this term gets reduced to 0. And here 0 minus 1 becomes what? 0 minus 1 will become square root of, that is 0 minus 1, and this will become root of minus 1. So root of minus 1 is nothing but j, right? So the value of roots are plus or minus. Here you will be having, in the place of this one I am having j. So plus or minus j omega n, and this term reduces to 0. So S1 comma S2 is plus or minus j omega n. So when you locate the roots here, so this is your real axis and this is your imaginary axis. One root is plus j omega n, which lies here, and another root is minus j omega n, which lies here. So here the roots are purely imaginary, right? Because it comes with the j and it lies on the imaginary axis. So the roots are purely imaginary, and this type of system is known as undamped system, right? So this undamped system is said to be fully oscillatory, that is the system which will oscillates continuously, and this type of system is not practically possible because whatever may be the type of system, it will have some amount of damping. But here an undamped system is one which never settle down, it will be continuously oscillating, right? So this is our first case when the value of zeta is equal to 0. And the next one is when the value of zeta is equal to 1. So when the value of zeta is equal to 1, again we are going to substitute the value of zeta equal to 1 here in this expression. So when you substitute, what happens when the value of zeta is equal to 1? So here you will be having S1 comma S2 is equal to minus omega n, right? Plus or minus omega n into, here I am going to substitute the value of del as 1. So 1 square minus 1, and this entire term will reduce to 0. So finally I will be having S1 comma S2 is equal to minus omega n. So here when you locate the roots, again this is your real axis and this is your imaginary axis, that is S1 is also equal to minus omega n, and again S2 is also equal to minus omega n, that is both the roots are equal. So here the roots are real and equal because the roots lie on the real axis. So the roots are real and equal. So for this case the system is said to be critically damped. That is, what is meant by critically damped? This system will have no oscillations, critically damped, right? And the next thing is when the value of zeta is greater than 1. So the value of zeta is greater than 1. When you substitute here, surely you will be having some values. So finally here for this case, the roots are real and unequal. That is, you will be having two different roots. So look here, one root is located here and another root is located here. And these two roots lie on the real axis. That is, the roots are real and unequal. They have different values. And the system is said to be overdamped, right? So this is also a type of system where no oscillations will be present, right? And the last one is when the value of zeta lies between 0 and 1. So when the value of zeta lies between 0 and 1, you see the roots will be, just here we are simplifying the value, that's it, right? So minus del omega n plus or minus omega into root of del square minus 1. This is your basic equation of roots. And here I am taking within this square root, I am taking minus 1 outside. When I take minus 1 outside, this expression becomes 1 minus del square, right? And again the square root of minus 1 is nothing but it is j, right? So Finally, our equation get reduced as minus del omega n plus or minus j omega n into root of 1 minus del square. So here in this case, when you write this equation, you see, you will be having one root as minus del omega n plus j omega n root of 1 minus del square. And another root will be minus del omega n minus j omega n into root of 1 minus del square. So these are the two different roots. So again, this is your real axis and this is your imaginary axis, and when you locate the roots, you will be having values like this. For example, I am telling just like this, plus 2 minus 2 plus 3j and minus 2 minus 3j. For example, okay, these are the two roots and I am locating here. So when you have roots like this, then the system is said to be underdamped system. So here the roots are complex conjugate. That is, one is with a plus sign and another is with a minus sign. And this system is said to be an underdamped system. Right. Hope you people understand this video. Thank you.